protons will move that way, and that's it. If you get polarization, that's the dielectric. Now, the diamagnetic is different. The diamagnetic, what you're doing is you're bringing a magnet, let's think of it as a north pole, against anything, again against anything, because what you have here is, again, atoms, and you have your electrons. Now, when you bring the north pole here, you're making a changing flux that the atoms see, right? And the atoms will respond, the electrons especially, because they're mobile, inside the atom. That's the interesting thing. Inside the atom, they will, if you have a, let's look at it, I'm coming at this thing, and there are electrons running around an atom over here. It will try to make a north, if I bring a north to it, it's going to try to create a north pole the other way. It's going to induce a north pole, and so by my first right-hand rule, the electrons, whatever motion they were doing before, they'll pick up an additional motion counter to the, and create a north pole on top of their ordinary atomic motion. In other words, they're doing the usual picture. You have an electron going around in orbit, or the quantum mechanical thing, a cloud of electrons, wave function, all that. But you'll superpose on that motion an additional circulation. That circulation will oppose the incoming changing flux. So every material will create a certain amount of opposing magnetic field coming out of this object. So you'll create a north pole coming out of this object, and that will repel the thing here. Sometimes, some people are thinking of this, if they can make it big enough, you could make a thing float magnetically. If you could have a thing which has a big diamagnetic effect, you could have like a magnetic railroad track, and you bring this very diamagnetic thing, and if the diamagnet is big enough and the north poles are strong enough, the things won't touch. So you could have a railroad car floating above the track, so you wouldn't have any friction. There are people who are trying to make a maglev, magnetically levitated thing using just diamagnetism, if you could get the diamagnetism high enough to oppose the weight. In principle, it should work, except that probably the weight is too much. Most diamagnets are not that strong. But you see, that's the idea. It's a diamagnetic levitation. You can also do it with permanent magnets in a way. You could have a railroad car, with maybe north poles. But then unfortunately that north pole is going to be opposed when you try to move the train this way. It's going to repel. It's going to be trouble. But you can maybe time it in some way that this becomes a south when it's over here, so it attracts the train. But then you don't want it to hit the track. That might be complicated. But the diamagnetic effect, there are articles about that. If you're interested, I can show you some. Yes. Lenz's law. Lenz's law says anytime I see a changing flux, I'll create an opposing field. It's Lenz's law again. Good old Mr. Lenz, he's just one of those stubborn opposing people. You bring a magnetic flux, you change the flux through here, it's going to induce in the atoms or in the molecules. Oh, I'll show you a very amusing case on that. So that's what the book, this is from the book, I think, but there's even more amusing things. So here is a table of the comparable things, electric and magnetic. We have the dielectric, we have the diamagnetic. The thing with the diamagnets is that they oppose each other. With the other polarization, the electric polarization, what happens if you have a plus here, it will repel the pluses to here, right? And so in a way, you get an attraction. With the diamagnet, you get repulsion. It's all straightforward from Lenz's law and Coulomb's law. You can go back to the basics. But the paramagnet is something we talked about before. Namely, it's a kind of material that has built-in, by structure, magnetic entities. Could be the nucleus of the hydrogen atom, the nuclear magnetic moment. So nuclear magnetic resonance done on paramagnets. Or you can have ferromagnets where the magnets self-align. And that's our big ferromagnets. And you can do ferromagnetic resonance too. That's powerful. I used to do ferromagnetic resonance. It's wonderful because you can get practically no material because it's all those iron magnets lining up. Instead of these tiny little nuclei with their little teeny moments that you struggle to see, you do ferromagnets, you take a little piece like that, and you get this giant signal coming out because it's a big magnet. So you can do ferromagnetic resonance where you take that whole big magnet and put it in a magnetic field, you put it on some sideways field, you get the thing processing. Fantastic. Yeah, it's a pleasure to work with it. So the thing is, where do these come in? Another place is that, for example, in a capacitor, we had the epsilon naught A over L was a capacitor. If you put some material in it, you could get what the capacity is because of this extra polarization. You get more capacity by putting stuff in it. Air has practically no molecules, so it's very small. Paper you could put transformer oil, they do. Glass, mica. But see what happens here? Water. This is what we said. Water is very polarized. So water is not an ordinary dielectric. It's a paraelectric. Right? We said water molecules have dipole moments, so the K that it provides is 80 compared to these little guys here, 1, 5, 1, 2. Silicon is pretty good. Germanium, there are 10, but water is gigantic. And look at these guys here. These are your ferroelectrics. So you put them in a capacitor, you get 100, 30, you get 300. See, as we said, these have big dipole moments, and they produce this big polarization, and you get a big multiplicative effect if you put one of those in there. Similarly, for inductances, we have formulas for, say, the inductance of a solenoid. If you put in some material in the solenoid, magnetic material, any diamagnet, any material, will give you some diamagnetic effect. In the case of water is not particularly magnetic. It's electric dipole, but no magnetic dipole. So it gives you this little effect, -9 times 10 to the -6, I see this here. About 10 to the -5 altogether. On the other hand, and it's negative. That means opposing. On the other hand, if you put in a paramagnet, even an ordinary metal has permanent magnetic moments. Namely, the electrons, the free electrons, they have magnetic moments. So if you put a piece of metal in a magnetic field, you will get a little bit of alignment of the electron magnetic moments. And that's paramagnetic. And then if you put in a ferromagnet, that's the big guy here, you can get a magnification of your mu by factors of thousands, like iron. And it was cute, though. I wanted to show you. Here's the physics of something nice. If you have these flat molecules, like benzene, you're familiar with, and graphite, imagine this. I have the molecule here. I put it on a magnetic field, as she asked a moment ago. Why does everything do this? Well, I bring in my magnetic field, and the currents are going to go around and create a magnetic moment opposing it, right? So suppose I have a flat molecule. Is it easier for the flat molecule for the currents to run this way or to run this way? Where are you likely to get the bigger effect? You see, if I have a nice flat molecule, I bring it here, the current's going to run around in the surface. If I bring it's trying to get a little current in the edge, sort of, so that you'll get a big difference between perpendicular, where you get big flow, and that shows up. You can do benzene in the plane. It's 3 times 10 to the -5. Oh, this is multiplied by 10 to the 5, so the number is -3 times 10 to the -5. But it's almost 3 times larger perpendicular. And graphite is the granddaddy of that. The big guy, it's in the plane, the currents can't hardly move, so you don't get a big moment. See, because the moment is a current times the area. Look at the area you got here, nothing. On the other hand, if you do this, you can get the thing floating going around this, you can get the current flowing around a big area, and you actually see that. The differences here is about factor 5 between the currents going, when you put the magnetic field, bring it in this way, you get these big currents running around, they can run around the whole area, and whereas if you bring it in this way, they just got to jiggle around, because there's very little coupling between the two planes here, because they're far apart. You know, you're familiar with graphite, that's why it's using pencils, because the planes are so loosely connected that when you write, you just rub the planes off. It's so loosely connected, that's your pencil mark. In fact, there's a new material called graphene, where what they do, have you heard about that stuff? What they do is they can peel off these sheets, these layers, one from another, and some guy got a bright idea, let me try to peel it off until I have one left. And I have a two-dimensional layer, one layer in 2 dimensions. You won a Nobel Prize. Because that stuff has some very unusual properties. When you get down to one layer, it acts very differently. I used to do that, and I never thought to go down to one layer. No, really, it's such an easy, you use Scotch tape. You just go like this, and you can just peel it off. And I stopped. Too soon. It's pitiful, you know. You kick yourself all the way home. It's just so think ahead, guys. I mean, maybe you'll do better than I. In any case, the other thing about ferromagnetism is they're all kind of different. Like iron, the magnets can hold together and form a permanent locked-in state up to a certain temperature. And as temperature gets higher, the spins start to get disoriented. Iron holds its magnetism up to this temperature, which is called a Curie. This is after Pierre Curie. This is Marie Curie's husband, who worked in magnetism before he met her. I don't know if she converted into radioactivity for some reason. It's not a bad idea, actually, but at the time. But it goes up to about 1,000 Kelvin. Cobalt, nickel, gadolinium, dysprosium is only 85 Kelvins. But you see, you can get some very nice, strong magnets. This is a strong one, samarium cobalt, up to about 1,000 degrees. Notice there's no iron in here, so it's a ferromagnet without ferro. Here's a ferromagnet without ferro. Here's another one. Gadolinium is nice too. Okay, so this is the Curie temperature, and you should understand that above that is paramagnetic, because they do have magnetic moments, but they're no longer locked together. Okay, so that's the story that I wanted to stop on magnetism and induction. Let me go over to Maxwell's story, if I may, quickly. And this is really a culmination of the course, one of the culminations. Maxwell put all this together. That's why I think that changing magnetic fields, the Faraday thing, is a red-letter day in science, because it changed the world, and we generate all our electricity by this process. And the other thing that changed the world is the discovery that there is such a thing as an electromagnetic wave, and that it's all around us all the time, and we depend on it. And the idea of understanding that was great. So this is the outline of the course. Basically, you needed one other feature to electricity magnetism that we hadn't gotten to yet, and that is the idea of a so-called displacement current. Once he had that, Maxwell invented this idea. Once he had that, he's a very good mathematician. He plugged it in, and he found that electric and magnetic fields could regenerate each other and create waves of moving electric and magnetic fields, which moved at the speed of light. Which he knew the magnitude of the speed of light. And here it was that electricity and magnetic, because we didn't know what light was up to this point. What is it, fundamentally? And when he saw that this kind of wave travels at the speed of light, he said, well, maybe light is electromagnetic waves. And soon afterwards, people created other electromagnetic waves directly using electricity and magnetism. Up to that point, they hadn't used electricity and magnetism to create light. Right? Because there was no light bulb. It was 1860. We didn't use electricity to create light. But somebody else, about 20 years after Maxwell, actually used electrical things like a capacitor and inductor and connected them together. And from electrical things, he got an electrical signal, electrical wave, sort of the way we'll do it. So I don't have the time we have. But the key thing is, very quickly, is that if you have, even if you have a capacitor here with empty space, somehow we're going to say that a changing electric field between here is able to produce a magnetic field just the way a current over here could. This is see, Maxwell had in mind two ideas. Hard to know what was in his mind, frankly, but he said a brilliant mind. But I'm guessing that on the one hand, he thought the electric field is stressing space somehow. And if you put on an electric field, maybe you create a kind of polarization of space. So you're displacing the current in space, the charges in space. Because then you would have a displacement current, even if it really couldn't get out of the space. But maybe, like I have capacitors here, the space gets polarized, and in a way, current gets across. Maybe it was something like this, or it could have been this idea that if you have a capacitor plate, and I use Ampere's law to say if there's a loop, and I go B times dr around this loop, it will tell me the current inside enclosed in that loop. I go all the way around the loop. But then you could use the argument like this. Now, is that a fixed thing? Suppose this, how do I know the current went through? Let me think of this as one of the kids' toys where you make a bubble, you have a ring, and you put soap, and you blow a bubble. So let me make a criterion. You're familiar with that, right? You ever do that? I do it all the time. No, so you put your soap bubble here, and then you blow it. And if the wire goes through, breaks the bubble, you say it went through the hole. So I blow a little bit of bubble here like that. Okay, that one's still good. Now suppose I make my bubble through the capacitor. Now the wire doesn't go through there. Now I thought I had current going through this loop. Over here, but over here it doesn't. It doesn't penetrate, doesn't break the bubble over here. So there's something missing in here. So by hook or crook, Maxwell came up with the idea that we will invent a current that's going through that space. All of these arguments are a little bit flaky, but the fact of the matter is that when you come down to it, you can say that, let us postulate, if you will, that there is a current, which we'll call the displacement current, in the space between the capacitor plates, which is given by epsilon naught times the electric flux. In other words, we know there's an electric field between here. So let me say that E times A is electric flux. Let me say that this changing electric flux will be a current, a displacement current. And it will be such a good current that it can produce magnetic fields, because currents, we know, produce magnetic fields. So in other words, just as this current here, which is a real conduction current, it could produce a magnetic field around here. Did I get that right? No, I got the direction. If the current is going this way, by I guess right-hand rule, the B will be coming out this way. just as that current can produce a field, I'm going to say that this current can produce a field in here. In other words, a changing electric field can produce a magnetic field. So another argument that you could use is that maybe Maxwell was reasoning by symmetry, in the sense that he knew Faraday had said that I can get an electric field, or an electromotive force, which is the integral of E dot dr, from a changing magnetic field. Let me try to see whether I couldn't get a B dot dr from a changing electric flux. Well, let me make it dt. Okay. You can almost argue, look, if you got one, maybe you'll have the other. And when he postulated this, he got the right. Then you can move on. So what you do is that you add to the Ampere law that the B dot dr is due to mu 0 I. You add to it that there's another current flowing, which is the rate of change of the electric field. And this is, as it says, the last of the electromagnetic equations. It adds to the Ampere law not only when the current is steady, but when the electric flux is varying. And when you do that, you have the four equations that how you create electric and magnetic fields and how they interact with each other. In other words, how B can create E and how E can create B. So those are the complete equations of electricity and magnetism, those how they're created and how they interact with each other. And so we write down these four laws that the electric fields are created. This is how we want to break that subject down. Sorry to keep it so long. But the electric fields are created by electric charges. That's Coulomb's law, or Gauss. And also, according to Faraday, you change B and you create electric field. And then, so there's the interaction of B and E. But the B fields are created not by charges, but by currents, which we say that there's no magnetic charge, but by Biot-Savart, you get moving charges create the magnetic field, or by Maxwell's thing, changing electric fields can create the magnetic field. So those are how fields are created and interact with each other. Then the second part, which I think I'm trying to break the course down into, this is how you create the field, and then you put something in it, and you get a force between them. And the force laws are the Coulomb force equals Q times whatever E was created up here, or you could have a moving charge or a current put into a B field. So that's the strategy of the whole electricity and magnetism. This is the pinnacle. This is it, the final synthesis of everything. And we have one more slide, or maybe two more slides on that, which writes down the equations. This is in your notes, my notes to you. And we can also get the interesting idea that you even have equations that work in empty space. Namely, if there's no charges or currents around, you still have something left. And when you have that something left, it turns out that you can generate waves from it. So I'm afraid I'll have to leave it there, and these demos we'll take up next time. So have a good weekend, folks.